Okay, Assalamualaikum and hi guys. So now we continue on part 2 of chapter 4. This part is actually specifically to show you how to diagnose a reactor using RTD. So earlier video we have shown you on how to calculate mean residence time, variance, all those stuff. So now we are going to use that mean residence time to diagnose your reactors, right? So RTD for diagnose faulty operation. In this figure, okay, part A, figure A and B is actually showing you the ideal operation of BFR and also CSTR. So this is the ET curve for ideal BFR, and this is ET curve for ideal CSTR. Okay. So you will see that if you have an ideal of an ideal PFR, it will be somewhere in the middle, the tau. Okay. So here you will see there's a pretty curve here, okay, showing non-tailing of the curve. But if you have a problem, normally we will only focus on dead zone and also channeling. For example, in the PFR, this reactor showing you two problem, dead zone and channeling, it will produce such kind of ET curve. And whereas for CSTR, it will both having the same thing, dead zone and bypass will show you this kind of curve instead of the ideal curve as shown in figure B. Right. So this also is example of the problem in the reactor. So you can see there's a dead zone in the PFR and also in the CSTR. Okay, short circuiting or bypass is the same thing. You can see the flow rate having a shortcut instead of going through all the catalysts throughout the bed of catalyst. They have a shortcut. Okay. Similar goes for this figure. So here you can see the dead zone will produce ET curve a long tail, and then compared to the ideal CSTR, this is ET curve having CSTR recycling. Okay, so now we wanted to identify modeling using IdeaRTD, right? So this is again your CSTR. Okay, perfect operation, okay, ideal condition, this is the ET curve. So you can determine your tau from the curve, okay. And if you have a problem of bypass, okay, instead of having the flow going through the mixer, they have a shortcut or bypass. So it will affect the flow rate. So when you affect the flow rate, so that's why it will be shorter here, the curve. And whereas the dead volume, okay, you will have some stagnant volume here. So that's why you will have 1 over tau SD higher than it's supposed to be, right? So now, in the tubular reactor, PFR, PBR will give you the same info, right? So if a perfect operation, when you plot ET curve, so you will produce this kind of an ideal condition. So you can determine your tau from the maximum height of the ET. It will be your tau. But somehow if your problem having channeling or bypass is the same thing, okay, so it will produce this kind of curve, this kind of plot of ET curve. And whereas for dead volume, okay, you will have this kind of ET curve. Okay, it's all about this formula. Tau is equal to V over V naught, where V is volume, V naught is volumetric flow rate. Okay, so if you have a channeling or bypass, if you look at this figure, if you have a channel or bypass, it will cause lesser volumetric to your reactor. Okay, it will involve flow rate, so you will have lesser volumetric flow rate. So when you have lesser V naught, so your tau will be higher. So when you plot your ET curve, that's why you will have your tau higher than the ideal tau, right? Whereas if you have a dead volume will affect your volume of the reactor. So the volume of the reactor become lesser. So when your V is lesser, your tau will go down as well. So that's why your tau, okay, that volume will be lesser than the ideal tau. SD stands for system for dead volume. SB is system for bypass. Okay. So just look at the formula. Okay. Tau is equal to V over V naught. So this is actually equals to Tm in the closed system. Okay. So this is the example to diagnose the problem occurred in the PFR. So let's say given to you this question. Okay. So 60 meter cube of PFR. This is the volume. And 0.05 mole per liter. This is your concentration. Okay. And then reaction rate of 0.045. Okay. And the volumetric flow rate V0 is 1 meter cube per second. So the tracer test was performed. So it will produce these two. This was the first or the past 2 years. The initial C curve will produce this kind of data. So you look that the tau is or more or less is around 15 seconds. Okay. So here, if you plot the C curve, okay, this is after 2 years. So the C curve, the tau has becoming 11. Okay. So we are only using the C curve just to predict, but the actual calculation need to be done to know exactly what is the problem or what is the actual condition of your reactor. So now given to you volumetric flow rate of 1 meter cube per second and 60 meter cube. So you can easily calculate the initial tau is 60 over 1. So it will be 60 second. Okay. So you need to calculate your TM based on this tracer data. Okay. So this tracer data, again, you need to calculate your ET first. You need to convert this C data to ET and then ET. Then only you can calculate TM. So I leave it to you to continue for the example. And soon you will find out that most probably, like what we have discussed just now, it seems that from the C curve, the tau has become lesser than the initial tau. So if we look at it, since it is PFR, so initial tau, it seems like it will have a dead volume. You see here, initial tau here, but when you calculate, when you see at the C curve, the latest tau is smaller than the initial tau. So maybe it will have a dead volume. So when you do back this example, using tracer data, okay, so most probably it will also produce the same problem. So I stop here for this part 2. So the final part, which is to part 3, to calculate the conversion of your real reactors, okay, and also the concentration, the exit concentration of your reactor. Okay, so that part will be discussed in part 3. So for your test will be until this part only, for up to part 2 of this video. Okay, that's all. Thank you.